Good morning, welcome to a new lecture. Today I will review virtual work method for beam and frames, and I will write a step-by-step procedure in order to solve those problems, in order to find deflection and rotation in the beam and frames, and I will introduce virtual work integration table as well, because in most cases integration will take a long time, so we can, instead of integrating those expressions, we can use virtual work integration table. Those tables you can Google it online, or you can find in the appendix of all structural analysis textbook. Let's first review what we had before. Virtual work formulation. For the deflection and the slope of beams and frames. Let's look at the formulation again, practice one more time, and then I will write step-by-step procedure. Assume we have one beam, simply supported beam. This beam is subjected to external load, any type of external load, something like this. Point A, for example point C, point B, and this is our external load, can be function of X. Here you can have another concentrated load, something like that. I want to find the vertical deflection of the point C after deformation, to see how much point C will deform down. So we know this beam will have sagging or deformation, something like that. I want to measure this deflection delta C. In order to find this using virtual work method, what we will do, we will have the same structure, we will have the same beam, because here we want to find deflection at point C. At point C, I will apply virtual load. If I want to find the slope at point C, I will apply virtual moment. Usually, we can put any magnitude to this virtual load or moment. The best way, the easiest way, assume it is 1. Assume the magnitude is equal to the unit, it is equal to the 1. If we look at 1, the small segment of this beam, the segment length is dx, and the distance from left support A is x. What will happen in this segment under the real load and virtual load? The same segment, it is very small portion of the beam, dx differential length for that element, and the distance from the left support A, it is x. You know the beam has cross section and we have neutral axis. For example, the cross section of the beam, it is rectangular shape, and let's look at the fiber in the distance of y from neutral axis, and assume this shadow part, the area for this element, it is dA. Let's see what is the stress in that element when we apply this virtual load. This virtual load will produce moment. Moment at this element, assume it is mv, m virtual, in that element because of the virtual load. I show it that with lowercase m. In that case, stress here will be equal to lowercase m times y divided by I. This will be stress in this fiber, stress times area for this shadow part will give us the force there. So the force here will be equal to m y over I dA. Stress times area will give us force. Here the stress, it is m, the moment, internal moment in this segment, in the dx, times the y, the distance of this fiber up to neutral axis, divided by moment of inertia will give us stress here in this level. That stress times dA area will give us the dF or force in this level, in this element. Let's see what will happen under the real load in that element. In real load, under the real load, moment in that segment will be mr, or I can show with capital M only. Both is right. mr means m real, or capital M usually they show, times y divided by I. What will be the elongation of that element? Elongation or deformation is equal to epsilon times dx, because we know strain is equal to deformation divided by initial length. Initial length for this segment, it is dx. Deformation there, if we assume it is delta, delta divided by initial length, which is dx, will be epsilon, or I can write delta is equal to epsilon times dx. From here, if I plug this term, because I know what is the epsilon. Epsilon, Hooke's law says sigma stress is equal to E Young modulus times epsilon. So instead of epsilon strain, you can put stress divided by Young modulus. So here I will plug, instead of epsilon, sigma over E, stress divided by Young modulus. We know all these, so I can write sigma divided by E dx, that will be equal to, instead of sigma you can plug from here, m y over E I dx. Now, what will be internal work? Internal work here, work means internal energy or internal work. It will be force times deformation. Force under virtual load here, it is this force. Elongation or deformation, it is my over ei dx. So, internal force will be equal to F times delta. That will be equal to m y square over e I square e a dx. Internal work will be force in that element times elongation in that element. F times delta. F we have here, delta we have here. We will plug, we will have capital M. It means moment under real load times lowercase m, moment under virtual load, y squared over ei squared dA dx. Let's see, I rewrite that expression one more time, and then what we can do. So, internal work is equal F times delta, that is equal to y squared E I squared dA dx. Okay, this is differential work. In reality it is dWi. If I want to find all internal work for entire beam, I should integrate that. It will be double integration of y squared over E I squared dA dx. I can rewrite this like integration of E I squared integration y squared dA dx. We know this term from static. From static we know integration of y squared dA, it is moment of inertia. So this part is equal to, again, I. So that will be equal to integration capital M lowercase m E I squared times I dx. These two I, they will cancel out, so it will be end up with integration m E I dx. What is the variation for dx? It is from 0, x can be equal to the 0 to L here. This will be entire internal work for this system. How about the external work? External work will be load times displacement. We apply which load? Unit load. So external load will be equal to PV times delta C. PV is equal to the 1. So 1 times deflection underneath of point C. Delta C will be external work. According to the principle of conservation of energy, we should put external work equal to internal work. So if I do that, what I will have? If I do that, I will have external work is equal to internal work. From here, I can write 1 times delta C, this is external work, is equal to internal work from 0 to L, capital M, lowercase m, E, I, dx. From here, deflection at point C will be integration from 0 to L, m, E, I, dx. We will use this formula in order to find deflection and slope in frames and beams. In frames and beam. For truss element we will have similar equation, but I formulate that later on. So for beam and frame we will use this formula in order to find deflection and slope. So let's write step-by-step procedure in order to find slope or deflection in frame and beams. Okay. Let's look at the procedure. I will write this procedure step by step. So you can use this step in order to find deflection or slope in any beam or frame. Let's look at these steps. Procedure. For determination of deflection in beams and frames by the virtual work method. Let's look at the first step. First step, in order to find moment expression or drawing the moment diagram, we should find the reaction for support. So the first step will be determine the support reactions in the real system using the equations of static equilibrium. This is first step. After finding those, we can find expressions for moment, or we can draw moment diagram. So next step, write an expression for the moment in the real structure and or draw moment diagram. You should pay attention the number of equations. Let's say add here note the number of the equations will depend on the number of the regions of the beam due to discontinuous loading. So maybe you will need several expressions for one beam and frame. Step number 3. I remove step number 1, I write here. So step number 3, create a virtual system by removing all the loads acting on the beam or frame and applying a unit load or a unit moment at the point where the deflection or slope is desired. So we will remove all external loads. We will create virtual system, means the structure is the same. We will apply unit load or unit moment in the point of interest. If we want to find deformation, unit load. If we want to find slope, unit moment. Then again, step 4, write the moment expression for the virtual system in terms of the distance x and or draw moment diagram. What you can do, if you write expression, you will need integration. That sometimes can take long time. But if you draw moment diagram, you can use the virtual work method integration table. If you use those tables, you can finish calculation much faster. So you can write expression for moment, you can plug in the formula and integrate. That is one way to do it. But depending on the moment diagram shape, they integrated before they developed table. So you can draw the moment diagram. So you have moment diagram shape and magnitude. You can use virtual work method integration table. So you can do calculation much faster. The last step. Step number 5. I will write here. Substitute the moment expressions into integration under real load times moment under real integration of moment under real load times moment under virtual load divided by EI times dx. You can plug those expressions in this formula and or use virtual work integration table. So first I will solve one or two simple examples using virtual work integration table. I did it using expression before, but today I will use table. So you will see how we will use those tables. Then I will solve several problems. Assume the simplest example. Assume we have cantilever beam and we have point load at free end. We want to find deflection at free end. So we have cantilever beam, point A, B, the length is L, EI is constant. We want to find delta B under concentrated or point load at point B. What is delta B? So what I will do, first I will draw moment diagram under real load. So the moment diagram for this system will be negative DLY. Moment at point B, it is 0, it is free end. Moment at free end always is 0 if we don't apply concentrated moment. So if we don't have any concentrated moment, external moment at point B, moment at free end, it is equal to the 0. From B to A, moment is increasing because P times distance will create moment. Because from B to A, our distance is increasing, so moment will increase, and that support A will be P times L. Why negative? Because this beam will deflect like this. Underneath of the beam it is subjected to compression. Underneath of the beam, compression means negative moment. Now, what is the virtual system? Virtual system will be the same beam. At point B, I will apply unit load. Why unit load and why at point B? Because we want to find deflection at point B, so we will apply load at point B. Because we want to find deflection, we will apply unit load. If we want to find the slope, we will apply unit moment. Here, again, the moment diagram will be the same because instead of P, we have only one So this will be moment diagram. Now I will multiply these moment diagrams because the formula delta B is equal to integration m over ei times dx. If we look at the virtual work integration table, you will see if the moment diagram under real load it is triangle shape, and under virtual load it is again this kind of triangle, and maximum magnitude both of them in one side. The coefficient for integration it is 1 over 3. You can look at those table. You will see it is 1 over 3 times the maximum moment here under real load PL. Of course it is negative. The maximum moment under virtual load it is negative L times the constant of length divided by EI will give us deflection. So this will be PL cube over 3EI. If you look at those tables, you can find those tables anywhere. You can look at the appendix in any structural analysis textbook, definitely you will find those. Or you can Google it, virtual work integration table, you will find it. Triangle, triangle, 1 over 3 times the length over EI. And these PL and L, they are the magnitude of moment under real load and virtual load. So this is about deflection. How about slope? If I want to find the slope at point B, what I will do? Under real load it is the same. Virtual load this time will be point concentrated moment, and the magnitude of moment it is unit moment I will apply at point B. In that case the moment diagram will be rectangular shape, again negative 1. Why rectangular shape? Because moment at point B, if we don't have this moment, it is 0. If we apply moment 1, it will be 1. There is no load until the end, so it will remain constant. And why negative? Because this beam, the forms like this underneath of the beam, we have compression. Compression under beam, it means negative moment. Now we will multiply this rectangular to that triangle. So theta B will be, again if you take the integration table, you will see rectangular to triangle, the coefficient is 1 over 2. So it will be 1 over 2 times negative PL times negative 1 times the constant of length over EI. So here the slope will be PL squared over 2EI. So you can use those tables instead of integration. If you remember, I solved this example using integration expression before, but today I used virtual work integration table. Let's look at a little bit complicated problems. Let's look at this system. Point A, point B. From here to here it is L over 2, L over, let's see now, this is L, and this is L. From here to here, let's say make a little bit shorter. So it will be L over 2. This part of the beam, it is rigid. Rigid means EI goes to infinity. The cross-sectional area is very big if we compare with other part. So A, B, C, D. Here we have point load P. For BCD part, the cross-sectional area is very big, so EI goes to infinity. If EI goes to infinity, it means no bending deformation, and we will not have any deformation for BCD part. But for AB part, EI, it is constant. So all deformation comes from deformation of the AB part. Let's see how this system will deform. If we apply this P here, this BCD part will rotate respect to C. So there is no deformation, only it will rotate like this. And we will have deformation for AB part, you see. So point B will go up, delta B. We want to find delta B. How we will find delta B? First, we will draw the moment diagram for real system. The real system is like this. If you find reactions here using equilibrium equation, for example, if I take moment respect to A equal to 0, and I want to find Cy. What is the Cy? Cy times 2L minus P times 2L plus L over 2 is equal to 0. I wrote equilibrium of moments respect to point A. So Cy times 2L. It wants to rotate this system counterclockwise, so positive, minus P times distance. It will be 2L plus L over 2. From here to here, it is 2L plus L over 2 is equal to 0. From there, I can find Cy will be equal to 1.25 P. Now, using equilibrium equation, equilibrium of forces in vertical direction, I can find Ay because Ay plus Cy minus P is equal to 0. From there you can find Ay negative 0.25 P. Negative means the direction is downward, so will be downward 20.25 P. These are the reactions here. Now let's draw the moment diagram. Drawing the moment diagram here is very easy. The moment here at point A, let's see, B, C, D. Moment at point D is 0, because again it is free end. Moment at point C will be P times distance. Which distance? That distance which is perpendicular to the load. So from C to D, that distance will be L over 2. So here the moment will be minus P L over 2. Let's I show here even. There I showed the reactions. Let's I show here. So it will be negative PL over 2. This is moment diagram for real load. So if you look at this joint here, the part BC and CD part, it is continuous and it is rigid joint. So we will have the same moment here. We should have it. Because this joint should be in equilibrium. Summation of moment in this joint should be equal to 0. Always in rigid joint. If we have, for example, moment M here, we should have the same in another side. Always is like that. Of course, if we have moment on the joint, it is different story. So here again, moment will be negative PL over 2. At point A, because it is hinge means no internal moment. The moment should go to the 0. There is no load on the A, B, C and CD part. That means moment diagram should be linear. It should be diagonal. It should be straight line. So this is our moment diagram underneath of real load. Why negative? Again, you see here after deformation, underneath of the beam, we have compression. So compression underneath of the beam means negative moment. We want to find deflection at point B. So what will be our virtual system? The virtual system, I should apply point load, unit load at point B like this. If I apply that, what will be the moment diagram? The moment diagram in that case, this ABC part, it is like simply supported beam, and CD part, there is nothing over there, so moment over there is 0. So moment here is 0, moment here. If I apply 1 here, the reaction will be half and half. 0.5 times L will be moment here. So the moment here will be, let's see, L over 2. Half times L will be L over 2 and it will be positive this time. Now, what will be the delta B? In order to find delta B, we should take virtual work integration table. If you look at that table, and if you look at that table, you will see for this part, this is moment, this is 0, 0 times moment, it is 0. So this part, it is not important. For this part, the moment under real load, it is negative PL over 2. Here is positive L over 2. If you look at those integration tables and you check, you will see if the moment diagram under real load, it is triangle like this, and under virtual load, it is another symmetrical triangle like this. The coefficient should be 1 over 3. So I will write delta B vertical in vertical direction is equal to moment here, it is, let's see, if you cannot find the table for entire one, you can multiply like this. Let's do like this. Because from here to here it is L, from here to here it is L. Let's multiply this triangle to this triangle, this trapezoid to this triangle. Even here, because EI for EC part from B to C, EI goes to infinity, because any coefficient we have for integration, we will multiply this PL over 2 times L over 2 times L over EI. Because for BC part, EI goes to infinity, that term will be equal to the 0. So even we don't need this part, because this trapezoid we will multiply to this triangle, and this BC part, it is rigid, means EI is equal to infinity, and we don't have deformation for that. So it is very simple. We will multiply only this triangle to this triangle. Here, from similar triangle, this moment at point C is PL over 2. So moment here will be PL over 4. Triangle, coefficient 1 over 3 times negative PL over 4 times positive L over 2. Let's say write like this. Coefficient for triangle to triangle 1 over 3. Moment under real load at point B, it is negative PL over 4. Moment at point B under virtual load, it is positive L over 2 times the length from A to B, which is L, divided by EI of the beam from A to B, it is EI. From here, answer, you can find it. So it will be negative PL cube over 6, not 6, 3 times 2, 6 times 4, 24 EI. So negative PL cube over 24 EI. Why negative? Because you see, from deformation, point B will move up. In virtual work method, the virtual system I created, I put unit load downward. If the answer was positive, it means deformation will be downward. Answer negative means it will be in opposite direction of unit load, so the deformation will be upward. So the final vertical deformation for point B will be PL cube over 24 EI. Let's look at another example. We have frame, very simple frame, like this. We have load at point P and load another load P here. L, E, I, L, E, I. We want to find delta A, B, C at vertical direction for this frame. How this frame will deform? This part will deform like this. This will remain 90 degrees. This will bend like this. Of course, I exaggerate a lot. Let's say make a little bit smaller. So, point B will transfer here, and then this will remain 90 degrees, this will bend like this. What is delta C? First step, we will draw moment diagram under real load. Moment at point C, it is 0 because it is free end. Moment at point B, just before B, if we cut it here, what is the moment? P times L. So it will be PL. Negative or positive? If I put dashed line like this, you see the deformation of the frame and you see the direction of the active moment P times L, it is clockwise. It will bend beam downward. So under the BC part we have compression, so it is negative moment. Joint B, it is rigid joint, we will have the same moment other side. At point A, what is the moment? At point A, moment will be P times L plus P times L. So it will go to the 2PL, again negative, because if you apply moment in this direction, you see P times L, it is clockwise, P times L, another clockwise moment, we will add together, so the resultant moment will reach to the 2PL, and that will create compression in the dashed line, so it is negative moment. This is moment diagram under real load. Moment diagram for virtual load. We want to find vertical deflection at point C. I will apply unit load at point C. The moment diagram will be at point C because it is free and it is 0. From C to B, if I move it just before B here, it will be 1 times L. Again negative. And because this is rigid joint, I will have the same moment other side L. And at point A, again moment will be 1 times L. So it remain the same and it will be rectangular shape. Now, how I can multiply these together? Triangle to this triangle, and coefficient for this triangle to this triangle is always 1 over 3. You can multiply rectangular to trapezoid, or you can convert this to the 1 rectangular, 1 triangle. Rectangular to rectangular will be 1. Rectangular to triangle will be 1 over 2. So delta CV will be this triangle to this triangle 1 over 3 minus L times minus PL times the length, which is L divided by EI, plus this rectangular to this rectangular. This rectangular height, it is PL, and coefficient for two rectangular it is 1. So plus 1 times minus L times minus PL times the length L divided by EI, plus this rectangular to this triangle. Now this triangle height will be PL, because the entire height it is 2PL, PL, we add together. So the triangle part height will be PL. The coefficient for rectangular to triangle, if you check those tables, you will see it is 1 over 2 negative L minus PL times L over EI. So the final answer, it will be equal to 11 PL cube over 6 EI. And I can double check my final answer. The coefficient, maybe I made mistake, but the procedure is right. I can double check everything. So, thank you so much for watching this lecture. See you next session. Bye bye.